and welcome to Answer Everywhere. Today we're looking at Bevy, a game engine written in Rust. And we were asked specifically to take a look at the entity component system. And I believe, based on looking at the Rust crate for Bevy ECS, that that's contained in this repo. We'll see. I've looked at other Rust repos before, but I don't know Rust. And I don't think I've really ever written Rust beyond Hello World. So I'm not super up on the syntax or even like a lot of the features. So we have this librs thing. It's the only thing in source. I'm guessing that's not the coolest thing. And we have assets, branches, crates, docs, examples, tests, and tools. Well, where's the code? Are there, let's see, branches? Maybe crates. Do we think they're in crates? Yeah. All right. So, Bevy girls. But we're going to look at Bevy ECS. I'll close these other ones. And what is it? It's an entity component system, custom built for the Bevy game engine. It aims to be simple to use, ergonomic, fast, massively parallel, opinionated, and featureful. All right. So, unlike other Rust ECS implementations, which often require complex lifetimes, traits, builder patterns, or macros, Bevy ECS uses normal Rust data types for all these concepts. Okay, so we're not getting fancy with the Rust data types. Components are normal Rust structs. The data are stored in a world, and specific instances of components correlate to entities. Correlate to entities. Are they entities? Okay, so we're going to use whatever Bevy ECS prelude is. And this position, I guess, derives components. I don't know what derive is. Perhaps maybe like implementing an interface or labeling it as something that can be stored in the component, some sort of component container. Worlds, entities, components, and resources are stored in a world. Worlds, much like standard collections, hash set, and vec, expose operations like insert, read, write, etc. Okay, we get a world, and I guess we stuff entities in it, or rather, components. So we know that components seem to live inside of a world, and specific instances of components are entities. So I guess if this is a position is a kind of struct, maybe like a type, and then instantiations of that type, I suppose, are entities. Is that the idea? Entities are unique identifiers that correlate to 0 or more components. So these are like inhabited types. If we have two components, position and velocity, you get a new world, which is mutable. Then an entity is going to be, we call onWorld, telling it to spawn at the origin with velocity moving 1 in the x direction and ask for its ID. So that's the unique identifier. And then we get a reference to the entity from, okay, so once we have the ID, we can look it up essentially in the world directory and get from the ref, we can get its position, which is a position type, and then unwrap it. Unwrap does what? I don't know. Maybe like unwrapping the pointer or reference or something. And then similarly with velocity. Systems are normal Rust functions. Bevy ECS can use function parameter types to determine what data needs to be sent to the system. It also uses this data access information to determine what systems can run in parallel to each other. So we have this print position, which takes a query And the query seems to be parameterized by entity and a position reference. And we're going to loop over those for entity, position, and query. We're going to print this stuff out about it. And then position.x gives us the x coordinate and y correspondingly. I don't know what makes that a system, but maybe that's a thing. Okay, so let's look at the implementation. We have compile fail. Is that interesting? Probably not so much. And macros and source. I don't know how, maybe if you're a Rust person, then you know whether macros are usually cool or not. Let's look at component lib, query data, query filter, states, world query. And then here's source. In source, we have entity, identifier, query, reflect, schedule. I'm curious about schedule. We'll open that up. Storage is probably important. System and world. Archetype. I don't know if that opened successfully. So change detection, component, event, intern. I'm going to guess is similar to interning like we saw in Zig. Label, lib, removal detection. Some reflection stuff. I think that'll be good. All right, so let's look at component.rs. Oh, this is macros. I think these were opening up, and I think I wanted to start at the end here. Except not with removal detection. Stop opening this up. Yeah, let's start with component. Okay. Source/component.rs. So we're using crate, self as Bevy ECS, archetype, change detection. I don't know what this directive is doing. I'm guessing this seems to be declaring something about our own package and maybe what we export rather than some sort of import statement. That's certainly standard Rust. I just don't know Rust yet. Pub use. Maybe pub is public. I don't know. But at any rate, this is a bunch of stuff that we're using or importing or whatever. And then this is a big comment. I like to see that. So pub trait component is some Rust trait, which I'm not really sure if that's different from like a type or an interface. And we've got this send plus sync plus whatever this static thing is. I'm guessing send and sync, these are kind of like, if you implement a component, it also implements whatever is in the send and sync interfacey stuff. And then this single quote static, I don't know, something about it being a static type maybe. So we have this comment, a data type that can be used to store data for an entity. Entity, I'm going to guess, is in brackets because that's going to maybe create a link to entity in the documentation, not because it's a list of entities. Component is a derivable trait. This means that a data type can implement it using a derive component attribute by applying a derived component attribute to it. However, components must always satisfy the send plus sync plus static trait bounds. Okay. So I think in type language, that basically means what I said before, that it can do the sendy stuff and syncy stuff. And it's a thing that you implement, I guess, by saying that you derive it. And whatever this stuff is. Examples. Components can take many forms. They are usually structs, but can also be of every other kind of data type, like enums or zero-sized types. The following examples show how components are laid out in code. And so this is probably similar to what we saw before. We're creating this struct license plate, which is deriving component. And we have this car, which is a component. And we have vehicle performance, which is also a component, which has acceleration, top speed, and handling. I've never thought of handling as being on a single continuum. Is that like bad to good? I don't know. Is that how people model handling? And then we have wheel count, which is also a component. And then for components and data access, see the entity module level documentation to learn how to add or remove components from an entity. So we saw that in the documentation earlier. And then we can choose a storage type. They can be stored in the world using different strategies with their own performance implications. By default, they're added to the table storage, which is optimized for query iteration. Okay. So maybe kind of like a database B-tree type thing, like a fast tree query iteration. At any rate, we're going to iterate over a bunch of stuff. Alternatively, components can be added to the sparse set storage, which is optimized for component insertion and removal. So this is like a sparse set. But to, I guess, get at maybe because it's sparse, it's hard to find anything unless you already know the index. And so there's different syntax for adding. Okay, so you can call a component storage equals sparse set. All right. As a consequence of the orphan rule, I don't know what that is, but something about orphans, maybe things that can't be reached in Rust. It is not possible to separate into two different crates the implementation of component from the definition of a type. This means that it's not possible to directly have a type defined in a third-party library as a component. It can easily be worked on using the new type pattern. All right. Well, that's kind of like Rust internals. And so we have this storage type. It's just some enum. We have a component hook. It's some life cycle hook, like on add or on insert or on remove. And whatever for W, for tier W, kind of looks like a tier. Single quote W, this function takes a deferred world of quote W into the component ID. That's just the type of the hook. It doesn't tell us like where the hooks are. Here's some world mutating functions. Component hooks. Wait, what? World mutating functions that run as part of the lifecycle events of a component. Okay. So hooks are functions that run when a component is added, overwritten, or removed from an entity. These are intended to be used for structural side effects that need to happen when a component is added or removed, and are not for general purpose logic. For example, you might use a hook to update a cached index when a component is added, to clean up resources when it's removed, etc. Okay, so what are the hooks? So on add, on insert, and on remove. Presumably into whatever storage you decide that you're using. And then that's the struct, and then we have these implementations. And on adds implementation is going to call self.try on add with expect, I think, is an error handling thing that says the component already has an on add hook. So I guess that's like the default failure mode. All right, we have this component info struct, which has an ID, a descriptor, and some hooks. So that's for each ID, telling you what it is and telling you where its hooks are. And then we have some implementations of those. And then this must be the ID because this is a value which uniquely identifies the type of component or resource within a world. Component ID is basically just a usize, but it's deriving a bunch of stuff like debug, copy, clone, hash, ord, partial ord. You can, I guess, put it in an order, a partial order. You can test for equality and partial equality, is maybe what it's saying. And it's, I guess, support for Bevy reflection. A component ID is tightly coupled to its parent world. Attempting to use a component ID from one world to access the metadata of a component in a different world is undefined behavior and must not be attempted. All right. And then we have the sparse set index thing, some presumably implementation of a sparse set. We have a component descriptor with cow, I'm going to guess is copy on write. A value describing a component or resource which may not correspond to a Rust type. I don't know what any of that means. More component descriptor stuff. We've got this drop pointer. X must point to a valid value of type T. Drop as T. I guess this is like casting a pointer, perhaps. What is new with layout? Create a new component descriptor. You're passing in a layout. Whatever a layout is, I don't know. This is presumably something about the way the memory is laid out. We have this public struct components, which has a bunch of components in a vector, some indices, which is a type ID map of component ID, and resource indices, which is a type ID map of component ID. And then we have an implementation. And just kind of on and on. What is a type ID map? So it's some Bevy util. I guess a map that I saw. It looked like we were getting the type ID presumably from Rust. Can I close this thing here? So when we call init component, the component has some type. This is looking like some kind of macro. And we're getting the ID of the type, which I'm going to guess is a Rust thing and not a Bevy ECS thing. That gives us presumably some sort of number. And we're going to, I guess, unpack self into its components, indices, and other things. I'm not sure. And then we're going to look, I guess, for each entry, for each index, given the type ID of the index, or insert with. I'm not sure what this notation is doing, but this might be similar to what we saw in Zig, that this is essentially a void function that we're passing in. We're going to set index to init component inner. This is maybe like the implementation function of init component, passing in component storage and component descriptors. And then on T, we're going to call register component hooks for, I guess, that type, passing in immutable components. Wait, what? We're going to register. We're going to at the index. We're going to look at the components and their hooks and call this registration function, which is presumably going to register them. And then index, I think, is just here to return the index, because I think in Rust the last thing in a block is the return value. But what did we do with the type ID? That's what I want to know. We passed it into the this indices thing. And indices is a type map. So I guess we're looking up from the type ID, the component ID is what that's doing. And then here's init component inner. We pass it in some components, some storages, some descriptors. And we get the component ID from the length of the components. Wait, what? Why would that give us the component ID? I don't know. But I suppose it does. And then we call component info and the component ID and descriptor. That gives us some an component info object. And then we check to see if it's in the sparse set. If it is, we call get or insert on the info. And regardless of whether it's a sparse set or not, we call components push onto the info. So I guess adding the info to the component, and we're returning the component ID. So what this is doing is it's just getting the so if there's like 4 components already in the list, this vector, then that means that indices 0 through 3 are occupied. And if we want to add another component, what it's doing is it's getting the first free index of the vector, which is the length. And it's just defining that to be the ID we're going to assign here. Okay. So let's see some other stuff. That's component. Here's event. Do we care about event? I guess we do. In a pub trait event, it can send and sync and also is static. A type that can be stored in an events resource. You can conveniently access events using the event reader and event writer system parameter. And we have an event ID that uniquely identifies an event stored in a specific world. You can copy it. We've got this ORD implementation. I didn't see this in the other file, but I assume that you have to do this anytime you derive something. That you have to say, if you say you can compare it, you have to define what the comparison operator is. We have an event collection somehow. What is it called? It's called events. An event collection that represents the events that occurred within the last 2 calls. The last 2 event update calls. Okay, so it's a pretty small cache. Events can be written to using an event writer and are typically cheaply read using an event reader. Each event can be consumed by multiple systems in parallel, with consumption tracked by event reader on a per system basis. So system is somehow the functions that operate on the entities. Events is implemented using a variation of the double buffer strategy. Each call to update swaps buffers and clears out the oldest one. Event readers will read events from both buffers. Event readers that read at least once per update will never drop events. And event readers that read once within 2 updates might still receive some events. And event readers that read after 2 updates are guaranteed to drop all events that occurred before those updates. Okay, so that's kind of like maybe a contract, an implementation, but I don't know if that contract is like specified in the types, or that's just the way that it's coded. So this seems to be some sort of default event. We have send batch, sends a list of events all at once, which can later be read by event reader. This is more efficient than sending each event individually. So this is just batching together messages. Send sends an event by writing it to the current event buffer. So we have some event buffer. How's that passed in? I guess it's not passed in, maybe. It's like implicit state, or maybe it's part of self. So we get an event ID, which is just the event count, like the next ID in sequence, whatever marker phantom data is. And then we have this detailed traces, which is possibly only run in debug mode. Although, wait, what? Event send. Oh, no, okay. This seems to be just some log statement. And then we're creating an event instance using the event ID and the events, just binding an identifier to the event itself. And then events b.push. This is, I was asking where where do you get the event buffer? It's just there's some reference to the buffer in events.b. So we're pushing onto some like array or vector event instance, and then we're increasing the event count. And then at some point, events B should be swapped with events A, right? Yeah. So here's a struct events. Holds the oldest still active events. Note that the a.start even count plus a length should always equal to events B start event count. So we have events A, which is an event sequence, and then events B, which is, I guess, holds the newer elements. And so what is events A used for? Is it only ever read? I don't know if we ever write to it. Oldest event count calls start event count, and min, passing in the minimum from the events B stuff. Okay. So update, I think this is events update. Swaps the event buffers and clears the oldest event buffer. In general, this should be called once per frame /update. So for every frame of your game, you should call this once. I don't know if it's your job to call this or if the engine calls it. If you need access to the events that were removed, consider using events update drain. And I guess update drain will drain the events and give you a reference to them. So we're calling standard memory swap. I'm going to guess this is atomic swap. And we've got self events B clear. So we're clearing B, and we're setting the B start event count to the self event count. And then we're asserting that the following are not equal. A start event count plus A length and B start event count. All right, so this is the thing that swaps it, that does the double buffering. We have update drain, and I guess that it would give you an event. So we're going to call, so I guess events B events.drain has its own thing, and that gives you some sort of iterator, which we call after, I guess, we've swapped it, which seems like a good idea for performance. We're getting the event count, asserting that those things are not equal, and then we're returning some iterator map of all the events. Okay. So that's cool. So that's events. I don't think we saw a list of possible events, but maybe you can send almost anything as an event. Actually, we can find out what the event struct is, right? Struct event. Event. Do we have a type? Public trait. Oh, it's a trait. Oh, yeah. It just says it has to have these types. All right, so I don't know what other restrictions there are on events. Maybe it can be any struct. Here's intern. Provides types to statically intern immutable values. Interning is a pattern used to save memory by deduplicating identical values. Speed up code by shrinking the stack size of large types and make comparisons for any type as fast as integers. Okay, so this is the interning stuff. We saw that Zig was doing the same thing. I don't think we really need to look at the implementation. Here's lib. I'm going to guess that lib is not going to be so fundamental. Maybe we can look at we have a bunch of module stuff and some structs, some tests. Things like function random access, bundle derive, despawn table storage, query all. Let's look at despawn table storage. Oh, it's a test. Okay, we don't need that. Removal detection, alerting events when a component is removed from an entity. I think we have a sense of how that would be implemented. Change detection. These are types that detect when their internal change data mutate. I'm guessing this is maybe just like a wrapper that you can add to types. Or maybe not. We have check tick threshold. Minimum number of world tick implements between check tick scans. So maybe they're just scanning on a clock. Change ticks can only be scanned when systems aren't running. So I don't know what a system really is, but so if it's world changing, so I guess it's game relevant, and this is maybe more like background computation. So I assume that sort of what it's saying is that when the things are running that really matter to the gaming experience, we don't do any of this scanning. Max change age, the maximum change tick difference that won't overflow before the next check tick scan. Changes stop being detected once they become this old. What happens after that? And then we have this thing, types that can change, that can detect their changes. So we have is added, returns true if this value is added after the system last ran. Is changed, returns true if this was changed, if this value was added or mutably dereferenced, either since the last time the system ran or if the system never ran since the beginning of the program. And then the last changed is, I guess, the ticket which it changed. Yeah. So let's see if we can find is changed. I guess we have to keep a reference to the old value or something, right? Or maybe we just have a yeah. How would we, if we're doing scans? Here's change detection implementation. So is changed is going to take the result of this and return it as a bool. We're going to look at self.ticks, and changed is newer than last ran or self.ticks this.run. What? So I guess we're maybe just ticks.changed will contain information about when it was changed. And we're just checking whether that is newer than other stuff we've looked at. Here's ticks mute. Added, changed, last run. So this is the data, I guess, that we're keeping track of. But I still don't know, like, how do you know if it's changed? So maybe if the memory was accessed or something. So ticks mute with this from tick cells. Deref mute. I don't know what that is. It seems to be dereferencing some pointer. So let's see if we like modify changed. Okay, set changed. So somebody has to call set changed, I guess. So who calls set changed? I don't know if that really counts as detecting your changes. If you're just looking up at it in some table, that there's something changed. But okay, so this is normally done automatically via the deref implementation. Deref mut. Okay, so I guess it is. They try to do it automatically. I don't know how that really happens. However, components and resources that make use of interior mutability might require manual updates. Okay. So this is really, set change is really for if you have to like override the manual thing. So normally triggered by deref mut or as mut. Here's the change detection mut implementation. Whatever this is, I have no idea what any of these symbols mean. I guess this is whatever the dollar signs. I don't know. This seems to be some sort of type, maybe nullable sized. I don't know if these dollar signs are like preprocessor or macro stuff, perhaps. But we've got this deref for name generics or whatever, and we call deref mut on self, and that gives us a self target, and we call set changed. Oh, okay. Just every time we're dereferenced, I guess we have some wrapping logic that calls set changed. And why does deref mut why does dereferencing it? I guess the idea here is that I think in theory you could get a mutable reference to the thing that's being pointed at, the memory that's being pointed at is, I assume, what's going on here. And in theory, you could get a mutable reference and not change it. But I believe what this is perhaps doing is that if you do get a mutable reference ever, we assume that it's changed, and we call set changed. At any rate, that's what I'm going to assume is the case. I'm just going to look at a few more things, and then I'm going to hop on to another repo, I think. So archetype are types for defining archetypes, collections of entities that have the same set of components. Collections of entities that have the same set of components. Okay. An archetype uniquely describes a group of entities that share the same components. A world only has one archetype for each unique combination of components. Okay, so what are some examples? I don't know. Edges. Checks the cache for the target archetype when adding a bundle to the blah, blah, blah. Let's see if there's archetype Bevy engine. An archetypal ECS. Archetypes enable efficient storage and processing of entities with similar behavior. Imagine we have a naive implementation of an ECS that stores components as arrays and entities as the index. Yeah, I think that's probably how this stuff got started. A gap in player, the gap in player and the gap in entity is very awkward. Sorry, in entity. Maybe enemy? If we wanted vectorized code to work on these arrays, they would present a serious problem. So here, I think is what it means. Is like you can't be both a player and an enemy. Vectorized code means that it operates on entire arrays or vectors rather than processing individual elements. Is that right? Yeah, okay. So SIMD. And so instead, I guess it's kind of like normalizing data. So now you have two things. One is the player archetype, one is the enemy archetype, I think is what it's telling us. Okay. And we've got this world query stuff. I'm just going to go through here. Schedule. I like scheduling stuff, but I'm not going to really look at it. Storage. I think that's about it. I think I'm going to stop Bevy ECS there. I'm going to take about maybe a 5-minute break, and then I'll be back and we'll look at another repo. See you then.